So let me continue from where we left. Uh, Now, if you see the dot product of two signals, psi 1 of t and psi 2 of t, we say that these two are orthogonals if their dot product is 0, and if these signals exhibits this property of orthogonality, uh, then we can define the two-dimensional uh, plane here using psi 1 of t and psi 2 of t as the two orthogonal axes. Now, let me recall the dot product of these two signals. If you want to find the dot product of psi 1 of t and psi 2 of t, you actually need to integrate the product of these two signals, and that should be 0 for these signals to be orthogonal. So, orthogonality is one property, and if this property is fulfilled, then we can define these axes. Now, if once you define these axes, uh, any vector drawn over here, any position vector in this two-dimensional plane. Let me call it two-dimensional instead of plane. I would say signal space, right? So we can uh, define any vector in this space, and that would be linear combination of psi 1 of t and psi 2 of t, uh, which is so we can write this vector as a linear combination of psi 1 of t and psi 2 of t. So this vector itself represents a signal s of t. This vector represents a signal s of t, which can be uh, a times psi 1 of t plus b times psi 2 of t, and this a and b are the coefficients, right? uh, or you can say the image, it's a scalar that represent the image of s of t along psi 1 of t and the image of s of t along psi 2 of t, respectively, a and b. So well, uh, here in the if you see this psi 1 of t and psi 2 of t, they are very similar to unit vector I and unit vector j. But there is another property. We just talked about the orthogonality property, that okay, psi 1 of t and psi 2 of t are orthogonal and their dot product is 0. Another property of unit vector is the magnitude of a unit vector, which is the suitable measure for vectors. The magnitude or the length of a vector is one unity. It's unity. Now, how to define the this property in these signal psi 1 of t and psi 2 of t? Actually, the suitable measure, if you recall your previous knowledge of communication system, there you have already studied that the suitable measure for signals is their energy. The suitable measure for the strength of a signal, the suitable measure for the strength of a signal is its energy. So we define the in case of signals, the dot product is defined by this equation, by this integral, and the energy of these signals, energy of psi 1 and psi 2 should be equal to unity 1. It should be equal to 1. And there are we will see with the help of an example that the psi 1 and psi 2 of t in a short while. So let's move to the our lecture notes and see these properties so that we do not miss anything. Now, in the signal space, extending our concepts or recalling our concepts of the vector space, we would move forward towards the signal space. Now, as you can see in this section 3.2, we have taken three signals, considered three signals, psi 1 of t, psi 2 of t, psi 3 of t, such that their energies denoted by E, capital E, with the subscript psi 1. Similarly, capital E with the subscript psi 2. These are the energies of these three signals respectively, and we say that the energies of these signals is unity. So it's very easy to define such signals, that the energies are unity, and very simple signal, a set of signals exist, which we will see in our example. So these two properties we define here, the energies unity, which are actually analogous to our unit vectors, with the unit vectors I, j, and k. Their length is unity. So here we define three signals, psi 1, psi 2, psi 3 of t, and we say that their energies is unity. So their energies will be unity. We here equation 3.6, if you see, we actually it define the energy of a signal. So it's a widely used definition that energy of a signal is the integral of the square of the signal. It's the integral of square of the signal, as shown. The energy of psi I, where I may be 1, 2, 3, because we have just three. We are just defining three signals. So I energy of psi I is equal to the integral of the square of psi I of t, as shown in equation 3.6. And the dot product can be defined as the dot product property is defined in equation 3.7. So if you see the dot product of these psi 1, psi 2, and psi 3 of t, it can be very easily defined using this equation, which says that the dot product of two signals, psi I of t and psi k of t, is equal to 1. It is equal to unity only when I is equals k, which means that when I equals k means if it is the same signal, then the dot product is unity. And if they are different, because psi 1, psi 2, psi 3 are orthogonal signals and three different signals, so their product, if I is not equal to k, then this product is 0. So it is actually a defining, it's a proper way, or we can say a fancy way of defining the dot product of two signals. So we have actually all the signals available. It's the dot product of all the signals available. You can just substitute 1, 2, and 3 for I, substitute 1 for I, 2 for k, or 1, 3, similarly 2, 3. You can just substitute I and k, and you can find out the dot product. So this the set of functions, these psi, which is represented by these brackets, psi I, this is the set of these functions. We have now three functions here, psi 1, psi 2, psi 3 in this set. So the set of functions which satisfy equation 3.5 and 3.7 are known as orthonormal basis functions. Now here the term orthonormal basis functions is used. Why? Orthonormal means these signals, this set of functions, psi 1 of t, psi 2 of t, psi 3 of t, these are orthogonal as well as normalized. Their energy is normalized to 1. So we say orthonormal. So these and these are, you can see, these are the time functions. So we call it that it's a these are functions actually. And why we call it basis functions? Because these provide they exhibit two properties, orthogonality and the normalized. Their energies are unity, and we can define we can define many signals as a linear combination of these three basis functions, these three functions. So we call it the basis functions, which we can define our signals as a basis function. Now if you go to this signal diagram, this signal space diagram, I think this would be it would be more meaningful right now, because now you understand psi 1 of t, psi 2 of t, and psi 3 of t, which are the three orthonormal basis functions, or the three signals. Now, and any vector, any position vector in this three-dimensional space would represent a signal, and that signal would be written as a linear combination of psi 1 of t, psi 2 of t, and psi 3 of t. Now, this figure shows an example for the three basis functions. If you see, very simple, very basic example. In figure 3.1, the basis functions are shown. Psi 1 of t, which is a pulse with the magnitude peak value 1 from 0 to 1, right? And similarly, psi 2 of t is a pulse from 1 to 2, its unity, and 0 elsewhere. And psi 3 of t is another pulse, which is unity from 2 to 3 and 0 elsewhere. These basis functions are represented mathematically, so you should be able to represent your basis functions mathematically, and you can see here just below the figure 3.1 we have three equations for psi 1 of t, psi 2 of t, and psi 3 of t, and you are familiar with this notation, which is equation 3.8. Psi 1 of t is 1 for t between 0 and 1, and it's 0 otherwise. Similarly, psi 2 of t equals 1 when t is between 1 and 2 and 0 otherwise, and similarly psi 3 of t is 1 between 2 and 3 and 0 otherwise. Another point to note is their energies. If you compute the energies of these signal, which means you square it and integrate it, you would find that the energy is unity. And if you try to find out their dot product, again you would find that the dot product is 0. Psi 1 of t and psi 2 of t, if you multiply these two and integrate, you would get 0. Similarly, psi 2 of t, psi 3 of t, if you multiply these two and integrate, you would get 0. So these are the two properties are already there in this set of basis functions. They are orthogonal, and their energies is unity. So I would like you to find their energies just to using this expression. I'll find the energy of one signal for you, and you would be you have to do it for the rest of the signals, right? So for psi 1 of t, if I try to find out the energy of psi 1 of t, so I need to integrate its square from minus infinity to plus infinity. I need to integrate this for psi 1 of t. So if I integrate this, you can see that this signal is only it is 1 square of 1 in this limit 0 to 1, and if I solve this integral, it is unity. So the energy of the signal is unity. Similarly, you can prove the energy for other functions, psi 2 of t, psi 3 of t. Try to find out these energies and also find the product of these two. It is clear from this figure. If I multiply psi 1 of t with psi 2 of t, you can see that psi 1 exists between 0 to 1, where psi 2 of t is 0. So the product here would be 0, and between 1 and 2 psi 2 exists, but psi 1 is 0, so again the product would be 0, so their product is 0. Graphically it can be represented. Do it mathematically in your notebooks. Now when you have these three signals, if you see equation 3.9, we can define a signal. These actually represent now the three axes, and any signal Sm of t can be written as a linear combination of these three basis functions, which is shown in equation 3.9. Sm of t is a m1 psi 1 of t, a m2 psi 2 of t plus a m3 psi 3 of t. So this is the linear combination, and if you see the vector of this signal as a vector in this three-dimensional space, you can view it in this figure. Now I guess I hope that everything shown in this figure is clear. You can see that the vector Sm, the vector Sm, which is a position vector, the signal vector Sm has three rectangular components along psi 1, psi 2 and psi 3, and these three are shown am1, am2 and am3. So in this is just one signal shown in this three-dimensional Euclidean space, or three-dimensional signal space. We call it signal space or Euclidean space, three-dimensional Euclidean space. So 3.9 actually you can it's very similar to your three-dimensional vector space, where you define as earlier we see that we saw in our previous slides, we saw that vector b was represented as a linear combination of I unit vector, j unit vector, k, and we had ax, ay and ak, ay, az, actually az three components. Here also you can see that it is very similar. The signal Sm of t is a linear combination of these basis functions psi I of t. These basis functions can be used to represent Sm of t as a vector in psi 1, psi 2, psi 3 coordinate system or three-dimensional signal space. So it's very similar to the xyz plane, xyz coordinate system, three-dimensional vector space. Let's move to the some more points here. The signal now it's very clear the signal Sm of t can be viewed as a vector, vector Sm, which is represented as bold, and the three this notation is used, the small brackets with am1 comma am2 comma am3 in signal space. So these three, just like xy coordinates we represent in two-dimensional space, just xy, because we have three dimensional space now. So we have three components x, y and z. So am1, am2 and am3, you have three components here. am1, am2 and am3 are the images of Sm over psi 1, psi 2 and psi 3 respectively, and any image, the image ami of this vector Sm over psi I can be evaluated using equation 3.10, which is now if you see this 3.10, this gives you the dot product of the signal with the unit vector psi I. So Sm of t is the signal, and psi I of t is the unit, just like that, the basis function. So